Good morning and welcome to the next installment in the Center on Aging Colloquium series on methodology. Today we will continue where we left off last time. So, but first, some information. You can forward your questions as you accumulate them during the lecture to Anne Greenwood or Vincenzo Gruposo. You see the emails on your screen. We'll start Q&A after the presentation. You can also follow the presentation and review previous lectures at the website shown on your screen as well. So if you would like to follow along or find GitHub files, source files, go there. So a little context as usual. This is where we are right now. We're in the third lecture on basic reproducible research skills. So just a little bit review what we did previously. We talked about the flow of data as it moves through the research process. We said that we start with raw files and try to create consistent instructions, consistent steps of what happens to this data so that we can recreate it whenever we want, so that whenever we have an issue about the model or graph that we would like to clarify, we have a clear record of where to find this. And we also said that the first lecture in the series on data manipulation was dedicated to tracing data from measured data to analytic data, preparing them to be graphed and modeled. The next lecture on graphs looked at this stage, and today we're going to naturally focus on the models. So in a wrap-up, what we did, and so this is sort of creates the floor for our today lecture. Again, a little bit of review. We load a data set that we've saved during our second, the first lecture, called DSL, right? It's in the state that it is ready to be graphed and modeled. Here's the structure of this data set. Here's the variables that we've included into it. So we've loaded that data set, and specifically we were looking at the outcome of religious attendance, right? So the respondents were asked, how often did you attend a worship service during the last year? And this is the possible category of responses that they could give. We treated them as continuous variables, and thus we're fitting continuous models to them, but they can also be treated as categorical. So once we sort of set that up, we've mapped this information, this data that we had in tables onto a graphical or dimensions of a graph, right? So we started with a very simple graph like this, and layer by layer, we developed the simple graph into a more complex visualization. And our second lecture went in detail how exactly we've accomplished these transformations, right? And this is the code that we ended up with, the final graph. So today, as we said, we're going to talk about modeling. So just to create the context what we're going to be talking about, there's two papers that I would like to recommend to get into the topic, and I do have to apologize if what I'm going to be talking today is going to be too basic. I'm assuming that there is no modeling experience in my audience. However, I know that many of you do have that experience, but I just wanted to be straightforward about that. So two papers that I recommend reading to get into this subject is one is called The Epistemology of Mathematical and Statistical Modeling, a Quiet Methodological Revolution by Joe Rogers. In that article, this thinking about what it is modeling as opposed to statistical paradigm of hypothesis testing, hypothesis testing. Well, the idea behind a model is that, there's many types of models, many definitions, but it essentially simplifies a complex reality. This is what it does. It's another way to think about this, or we can think about this, is a mechanism for reproducing data. Another aspect of a model is that it operationalizes a substantive theory. Now, in here, I'm not trying to give a deductive definition of model, right? I'm not trying to generalize. I'm trying to define model as it is relevant to our particular immediate needs, and then we can sort of take away the messages, what modeling is and what isn't. So what does modeling, as I define it for this project, involve? What does it involve? Well, as we defined through this, the initial definition, a model is a mechanism for reproducing data, for generating data. So it generates data points. Well, that's one thing that involves modeling. We generate data points through some application of some algorithm. Secondly, we compare observed and modeled data, right? So we generate some data and then we compare the data to the existing one. We also describe the properties and attributes of that comparison, right? When we compare the observed to the model, we have interesting properties emerging from that. We can describe the difference in interesting ways. And finally, when we have a series of those descriptions of how the model predictions differ from the observed one, when we have a multiple of those comparisons, we can compare the comparisons and start comparing and contrasting models. And hopefully that's that stage in the process where we arrive at some meaning behind our theories, behind our hypothesis, or we're trying to make sense of them. The second articles that I would like to mention was written by Linda Collins in 2006. It's called Analysis of Longitudinal Data, the Integration of Theoretical Model, Temporal Design, and Statistical Model. She offered in that paper a conceptual framework to approach longitudinal research. And she said, look, we have to combine three elements in our narrative of research. First, we have to think and describe the theoretical model of change. And that, what we mean by that is what shape of change we expect in the phenomena, what scale of change we expect in the phenomena, right? If we expect something to decline gradually, but we apply models that look at sudden changes, apparently the theory behind what we're trying to find is incorrect, right? Such things as periodicity is also part of that. If we know that this phenomenon has some periodic property to it, we have to include that into our theoretical model of how something changes, how a phenomenon changes. Temporal design reflects the data, right? It reflects, in a very particular aspect of data, timing, right? So when the data was collected, how frequently was it collected? Is it panel data? Is it intensive data? How were observations spaced? Were they spaced equally? Was it spaced in random intervals? How was those data points acquired? And finally, statistical model of change, as we mentioned before, operationalizes our theoretical model of change. Now, the fit between the theoretical and statistical model of change, it seems to me, is in the hand of the people who argue, right? So if it has to have high face validity to have a match, and it's sort of on your shoulders to demonstrate that you have an adequate match between statistical and theoretical model of change. So with that context laid out, let's delve into what I call the prelude to modeling, because since modeling is so intimately connected to data, first I want to take a look at how we can represent data so that when we come to modeled data, we have a richer vocabulary of expressing both ideas and concepts and models and so forth. So let's look at this screen that you've already seen a number of times. Right now, I want us to recognize that we have data represented twice in two different forms, right? One, it's represented here in a tabular form, and on the right, it's represented in graphical form. I would like to add another form, another way how we can represent the same data to here, and that's algebraic, right? So if here we arrange variables in columns and time and individuals in row, well, in this time there's only one in this case only one individual, right? Here we refer to the rows and columns of these variables or dimensions through indices 1 and t. Well, this is actually a projection from a data structure called data box that was proposed by Koval in '66 and '86. Those are two editions of a handbook of multivariate statistics. So the Koval's data box combines or operates in three dimensions: occasions, variables, and persons. And that structure helps us, or is very convenient to express majority of design situations in social sciences. So that's a very powerful and flexible structure. So here we see that in the tabular form of expressing data, we have a projection of a three-dimensional data Koval's box into two-dimensional space of a table. And we see that the way it accomplishes it, we outsources the third dimension into the additional variable ID, right? So we see how this tabular form adjusts and represents that three-dimensional structure of Koval's box in a two-dimensional space. Well, here we also have a different projection of the same information, also in two-dimensional space. And we see the correspondences, that the graph did not change. So now we would like to see how we can represent with algebraic form a different person, right? So as I alternate between the slides, you can see that the index here changes from 1 to 2, indicating that now we're representing data for the person with ID number 2, and we're representing all data points for all times t, right? So this is person 1, this is person 2. We can also represent it person 3. It doesn't have many observations, and 4, right? So with the same success, we can change this t index to pinpoint to the particular observation, right? So if we say y43, it means that we refer to the data point taken from a person with ID number ID 4 at t time 3. So this becomes a very succinct, very powerful way to represent every possible data point in our study, right? So we're getting into this idea where we're getting used to representing information in different ways, and we'll try to bear fruit, get fruit from that. Okay, so let's see how each of these ways to represent data deals with adding additional dimension to this, right? We've said that we've taken that Koval box, the three-dimensional structure, and pressed it in or projected in two dimension. And we've seen how we have three ways of projecting them into two dimension. What was going to happen when we have to use third dimension? Okay. So the tabular form deals with it by adding a different, another basically chunks of data, right? So it stacks the individuals on top of each other and thus preserves the two-dimensional way, but it's really three-dimensional now structure. The algebraic form uses the subscripts I and T to represent person and occasion dimensions respectively. Okay, and we see that the graphical form just plots everything on the graph. So we're beginning to see that these different forms of representing data have different potentials for, first of all, seeing things about the data, and second of all, communicating those things about the data, and also using them about applying them, right? So if you would want to quickly see something, you would go for the graph, but if you want to think through possible combinations of variables or whatever or whatnot, you might want to use an algebraic form for that. Another important conceptualization of a model comes from John Tukey, who conceptualized data as model plus error, or also the so-called principal equation of exploratory data analysis formulated in his famous Orange book, says that data equals model plus error. It's the same thing as data equal fit plus residual, or we can think about this in graphical way as rough plus smooth, right? So when we fit a model trajectory, it's smooth because it uses less data points. It's a approximation to the data points. So this trajectory, the observed trajectory, is jagged, but if you fit and try to predict this trajectory, the line would be smoother. Okay, and that's the famous textbook that I referred to. Okay, so this idea that we can take information recorded in the values of the data and decompose it into two components. The one that represents the model, what we're after, and another part that represents error, right? That we can also find ways to use. Okay, so now let's actually start modeling. So the purpose of the model is to recreate the pattern in the data. Now, if we're working with three different ways of representing data, we can model data in any of those three ways. So one of the most apparent and probably easiest way to model the graphical data, I just take a ruler and try to draw a line that looks like the line that approximates the data points. Is that going to be the best modeling method it's possible? Probably not. It's not going to be as accurate, but it's doable. That's the point of a model. You recreate the data, and the quality of that recreation, of reproduction, is going to be the value of your model. And also the interpretation that you can give to the method with which you use to recreate the data is also going to be a part of your argumentation, right? So let's see how we can recreate this data in this example. So we're starting very low, and we're saying, well, the data generating mechanism, the mechanism that we use to cast prediction, is going to be very simple. We're going to say that Y, and we're sort of, when we're approaching this question, we're asking, well, we need to model the data. That is basically to answer a question, what should Y be for the person 1 at times t? What the value of Y should be for this person at every time t? Well, this model that we're fitting says Y should be 4 for person 1 at all times t. Is that a good model? Probably not, but it is a model, right? It does what the model is supposed to do. It says what the value should be for that time, for that individual. And we can, maybe our substantiation for that I saw it in a dream last night. My dead grandmother came to me and said that this model should be 4. It's a bad example, it's bad substantiation, but it is a model. So another question that we can keep in mind when we're trying to achieve what model's supposed to achieve is the question, how can data be simplified, right? That's the purpose, the teleological goal of model is to simplify data. And that simplification is valuable. It could be dangerous, but it's also the value that we pursue in this exercise. So the next way how we can advance or make our model a little bit more complex and more sophisticated is we can add this element. See if you can spot the difference in the code as I alternate between the slides, right? So here we said we define our model to be 4 minus DSM, dataset DSM variable time. So it translates into human language, y should be 4 for person 1 at time 0, right? And then decline with each occasion by the value of time variable. So we take 4 minus 0 equals 4. We take 4 minus 1 equals 3. We take 4 minus 2 equals 2, and so on, and so on. Well, it does look like if you would fit an average trajectory through these data points, you would get some decline, but that decline is not as sharp as I think it should be. So the way how I can moderate that decline is to add a constant, multiply that term by a constant. And this is what I will do. And I will say, well, y should be 4 for person 1 in time 0, and decline with each occasion by the value of time variable multiplied by a constant 0.2. Well, that looks like a good approximation to what's happening here. Well, by looking at it, again, we just did modeling without really knowing how to do modeling, right? We just try to predict what the value of y should be by whatever means necessary. Well, if we can do the same thing for maybe different people. So this is the subject with ID number 2, and I decided to guess what his trajectory might be approximated as. So, well, maybe that's a guess. Subject number 3, another guess that I took. Subject number 4, oh, okay, that one. Well, what if we have all 4 subjects? How would we guess? What do you think there would be a decline in this or increase in here? I would guess a decrease. There's more. So I would guess something like this. Right? But of course, there's a way to find out for sure. We can actually compute the best fitted line using least squares or maximum likelihood. The estimation of the model, it's a technical part, right? We can put it off until we have more time to talk about this. But right now, we don't worry about this. What about this? We're representing now, there's going to be less than 300, but we're taking every individual, well, actually, yeah, we're taking up to 300 individuals from this data set and trying to plot them in this graph. At this point, it looks like it's going to be probably declining, but I don't know how fast. It becomes really difficult to see the average picture. You can see, maybe a lot of movement right here as a transition, but it doesn't. You cannot see the individual trajectories to say what's going on here. So, well, this is as good guess as I could give you. So let's, instead of guessing, we can estimate the model, and this is the next step in our development. So in here, let's look at the, we already see and familiar with this code. We define how the data set with which we're working is defined in terms of our data stage DSL. In these two highlighted lines, first let me, we define or create a new object called model, and that object retains the results of the function GLS in the package NLME, right? And again, once again, this is a syntax of this of our commands: package double colon function name, and this function writes the formula of the model that you would like to fit, and it says that attend. Right? Attend, this is our y, this is our outcome, equals 1, or intercept. Right? And we have, we're rewriting this in algebraic form with the following formula. Okay? So when we execute this line, it creates an object that contains the results of that model estimation, but we still don't see it. We're not seeing it. We don't have it ready. So in order to sort of get to peek inside, we have to exercise a little additional steps. So we would like, if we type in model and print this object, this is what it would give us. It would give us the, recreate the formula that was applied to estimate the model, give us log a likelihood, and give us the solution, which in this case is going to be 2.477. Now that we have this object that contains the results of the estimation, we can interact with this in ways to enrich our analysis. One of the ways how we can interact with this is to use predict command. When we assign, so in this line, we run a statement, create a new variable or create a new column in dataset DSM, and make the value of that variable to be the predicted values using the estimated, using the results of the model estimation. Here's the fitted model in which we use not only the intercept, but also the slope of time. Once again, we can print this object model to get a little bit more insight on what it returned. So again, we see the log likelihood and we see the coefficient values. The intercept went up a little bit, and as predictable, as understandable, the slope is negative. Once again, we defined this column of data as the predicted values of our model, and this is that comparison I was talking about, the comparison between what we observe in the data and what we predict with our model. So which model is better? Of course, you've sensed the TLL, the trap here. We need to understand what criteria we would like to use to evaluate the statement, and also what criteria we do not want to use to evaluate that. We also may have different preferences in the fit and parsimony tension. Sometimes we don't mind having a little bit less fit if we have better parsimony. Sometimes the other way. In any case, it's a complex judgment, right? We have to input a lot of information in order to make the judgment, and it never really easy. So there's two distinct challenges that I would like to focus today, that I want to talk today. First challenge is, how do we collect results from these models, right? So in this case, we have only two, but imagine we have many of them. It does become another data processing challenge that we need to face. More specifically, what pieces of information do we need to keep? And that's not a trivial question, because there's a lot of information there. So we need to identify only those pieces of information that are relevant to our project, and that, that we don't want to keep the information that we don't need, because that will punish us. That will overwhelm our cognitive abilities, and well, it's going to be competing for our cognitive abilities with the imported information. The second challenge is, how do we, let's say we've identified what we want to compare the models on, right? We say, well, we'd like to have our deviance, we would like to have our BIC, AIC, and estimates. How do we organize those comparisons so that we don't suffer from information overload and don't lose the information we're trying to recover from those comparisons? When you have two models, it could be easy. When you have 10 models, it could be a little, much more difficult. When you have 50 or 60 models, it becomes an ordeal. So today we'll look at what are possible solutions the technology offers us in this challenge. So first of all, I'll show you and give you examples so you can use it in your work. How do you recover the information from a model once it was fitted? So the highlighted lines show, again, we just create basic data set. This is a very similar definition of a data that you've seen before. And now we define model A as this formula. So this is just it's a linear model with intercept. And we put the predicted value generated by that model in column model A. And we do the same thing with model B. And here on the right, I have a little bit more, well, the same general sort of summary of what this model is, but with in a separate sheet, we have a more detailed summary of this model. And we, again, interact with this object called model A that we created by the GLS function using a function summary. And as you interact with these objects called S3 and S4 objects, basically list objects generated by model fitting routines, you will learn that the products of different functions give different objects, and you sort of have to know their inner structure to retrieve the information effectively. And there's slightly different vocabulary that you will have to pick up to interact with these objects effectively. So this particular function summary that you can pass to which you can pass the S3, S4 objects, give us a little more information. It gives us AIC, BIC, log likelihood, which is the sort of raw deviance, right? So log likelihood times -2 gives us deviance, the measure of deviance. We have extended coefficients, so we get standard error, t-value, and p-value. So we see that intercept is significant. Well, surprise, it is. It should be significant. No surprise there. Standardized residuals, residual standard error, degrees of freedom, much more than the general summary. Now, there's in the previous slide, there's a link that you can follow that will take you to the description of this function. You can see what other options you can use in your own fitting. Again, you've probably seen a function called LM, linear model, maybe in my previous demonstrations. It works very similar to GLS. The difference is that in GLS, that stands for generalized least squares, we can make arrows correlated and be independent, and LM does not have that. So this is technical. You can read this on your own. Okay, so we've got two objects, right? So we're trying to demonstrate how we can compare models effectively and what's involved in comparing models in R. Using an example of two models, model A that contains intercept only, and model B that contains intercept and the slope. So we'll take model B and we'll start interacting. So we'll start collecting, retrieving data from this. So in line first, we just assign, rename the object so that we can pass the same name and repeat this code to the model of a different name, and we don't have to retype the code inside. So for instance, right here, we see that you pass object model to these lines. Everywhere you pass model, model, model. If you wanted to use the same sort of code to a different object, if you did not have this first line and specify the commands in terms of the object model, you would have to rename. You would have to put model B here, and then you have to put model B here, and everywhere you see model, you have to put model B. And when you change the model, then you have to change the name of that model. So in order to avoid that, we just create a sort of a substitute and pass the substitute, and then rename it whenever necessary. Just a little trick that might save you a little time on typing and keep your code a little cleaner. So let's look at it. We have, so log likelihood, we can attain log likelihood by producing the summary of this model and then taking an element from this summary that is called log likelihood, right? That's another way of retrieving information. First, you create the summary object from the original object, and then you take that object and find the element that you need. Could be a little bit convoluted. AIC, very simple. It's called AIC function, BIC. DF residual, we will keep it just to keep the structure. We just want to have a slot for that. N, once again, we see this summary. First, we produce the summary object of the model, and then we take an element from it, and then we take another element from it. You see how this is sort of enclosed lists with inside enclosed lists. So it could be challenging to dig inside and find the information that you need. But that's what makes R really powerful, because you can have access to that information. Degrees of freedom residual, we can calculate it from the elements that we've received before. And here I'm pulling all of these quantified indices of model performance, of model fit, and I put it in a single data set called minfo. Then I transpose this minfo because it has the shape that I don't need. I need a slightly different change. And finally, after I did all the sort of cleaning of this data set, I store it in the object called MB. And when I print this object, this is what I have, right? So I have a list of indices that somehow describe the model. And frequently you would hear people refer to this as the model, right? Because this is the solution if you add the coefficients. That's the solution to which your per problem solves to. Let's see what model A. If we do the same thing to model A, we see that, well, log length change right? Deviance becomes larger. AIC becomes smaller in this. So in model, oops, B. All right, so we start going back and forth. Do we get the, yeah, we got a more full, so we can compare model A and model B, and again model A. So apparently everything that you need to know, or at least let's assume that everything that you need to know about the models is encoded into these images, or in these tables, in these indices and numbers. Does it mean that we understand what's happening? Even if we put this into table, right, or we just combine them together and we produce these nice looks, we can see how model B, as model B, because model B is more complex, it's supposed to fit data a little bit better, and we can see that yes, the deviance, the total amount of discrepancy between the fitted and the observed data goes down, and AIC and BIC are indices that show, well, by how much do they go down compared to the amount of information you put into the model, right? According, fit and parsimony intention. So organizing comparison, when we have only two models, this is relatively straightforward, right? We have, if we know the interpretation of AIC and BIC, we can answer simple questions. Does model B fit data better? Or model A fits the data well enough that it doesn't benefit from additional complexity very much. So no, thank you. We don't need to fit that slope. It's too expensive. If we want to, if there's more models than two, if the models that you fit are not entirely clear to you and you need to try models that you're not sure about, and you want to maybe try models that you have no confidence in, you just want to see how they misbehave, right? When you have that sorts of needs, you need to get inventive. So one of the ways you can help you organize comparisons is through what I call model manifestations. We've already talked about this in this lecture. There's many ways to simplify pattern in the data. Each has its own advantages and its costs. So, for example, we have a tabular form of both. We have data, and we're representing how we recreated the pattern in that data. We can also put it in algebraic form. We encode the same information, or not the same information, but the same idea, right? We tell them, we write the instruction of how to produce the numbers in this column, right? So even we don't have these numbers, if we express this in algebraic form, we will get this. If we fit this form, we will produce these numbers. We can also express it as a model fitted inside some estimation routine, right? So this command is highly meaningful because it takes these data, right, these attend data, and turns them into the predicted values, right? So this is the command that you tell the R what to do. We can also speak about or express model as the collection of all the indices and all the coefficients, and we call that a model, right? We can also express the same idea, the same information, the same concept as a graphical representation. And that has a benefit because we put every data point on the line. We see every data point, unlike tabular form, unlike numeric form, unlike algebraic form, that hides them inside the structure. Well, but graphical is not very good when we're trying to understand what are the structural relationship among the elements. So we resort to schematic representation. In this case, we have only 4 time measures. I didn't have space to put all 12 time points, but we can do that, and we can be specific. Again, if these schematic representations are good for one uses, but not very good for others, and having more expression ways to express a model is very beneficial. Finally, we can simplify the patterns in the data by simply transcribing it into human language, and that's also highly valuable. So we can say that, well, describing what's happening, we say in 2000 respondents attended church less than once a month. So the value that on that scale is 2.79, and gradually declined in their attendance ever since by about 0.06 per year, right? That statement is also a model. It simplifies some patterns. It does it probably huge injustice in terms of fidelity of representation, but it encapsulates the main essence of that in a structure that you can say in 20 seconds. That's certainly has its own uses. So the takeaway message from here: when we have multiple models, when we have very complex comparisons to conduct, the more ways in which we can express a model, the more potential for insight we can get in analyzing these models, and also the more, the better we can handle information overload, because the flexibility of changing model expression leads us to the expression that is the most convenient for a particular purpose. So next time, we'll be looking at very specifically how to use dynamic reporting to address 2 practical problems in what we've just arrived to. First, we have a problem of how do we present each model? And second, related to that, is how do we construct a sequence of models to analyze? And what I mean by that is, I'll try to illustrate in this example. So I fitted, for my dissertation, I fitted a number of models . So this is one of the ways how we can address these issues, and I'll show an example, and we'll work through example of how to create something like this next time. So I used the same data that we're talking about right now, and I fitted a series of random coefficient models. Well, in this particular case, I started with a simple linear model without any random coefficients, and this is what I chose to keep. This is our algebraic representation of this model. Here's our numeric representation of our model. We can see t-value and standard error and estimates. So apparently this is this intercept term, and we can see tau elements. And right now it's zeros, but when we allow our random terms to correlate, this would become important. And we also see the standard deviation of our residual. Again, this is the problem. How do we express a model? How do we choose what goes into representing a model? So as I start, let's focus on this algebraic representation so we can understand how we develop this sequence. I'll wait for that, of course. Oh, come on. So as we click on the next models, we add elements, And even though maybe you cannot follow the algebra so far, but you get the idea. We add elements to our model, fit it, analyze it, and try to understand what happens. As you see here, this is a graph of fitted data, right? So I take these numeric model solution, pass it through the create predicted data points, and plot them here. This is an overall graph of model misfit. So this is a deviance of all models that I fit, and you can see that the list is rather huge, right? So you can go through many of these, and this is a sort of a mini map that has the model names that are being under the microscope right now, so that I can remember the names of and look at the models later. So we're clicked through the models with no random components. So now if I go and I start with this basic model and I start adding random components, I can understand what these models have in common. You see how going from here to here is these models are nested within each other, but also these models are nested within each other, right? So you can take one model, take a step modifying that model, and arrive at a different model that at that time would have another sort of ways to deviate from that, to develop from. And that's the challenges that I spoke about, right? We have to, not knowing the end result, we have to decide two things: how many models we would like to aggregate into some meaningful sequence that we can look at and define and understand in terms of each other, and at the same time we have to decide what are the dimensions, what are the indices that we're going to be looking at. Are we looking only at coefficients? Do we need to look at the standard errors or not? If we do decide that that's important, if we have too many of those, that's gonna charge our attention. We might lose something if there's too much information. So it's like you have to solve two equations. You don't know anything. So you have to try to based on experience or based on trial and error, to arrive at some common state, so that each model in a sequence, and right here I have 52 models, each model could be expressed in the same dimensions so that they can be placed next to each other, and you can get from any model to any other model through a series of model development steps that you go through one nested model to another nested model to another nested model, and thus you can start judging what steps in model development lead to better, higher predictability, more error explained, more elegant solutions, so more elegant interpretations, and so forth. So we'll try to see how, using this new technology, this fairly recent language R Markdown and knitter package, R package knitter, we can create a sort of virtual microscope or virtual machine for examining the results of many models at the same time, that will enable us to insights that we would not probably have otherwise, simply because there's too many models. The problem of organizing those comparisons is too burdensome. And that concludes my presentation. If you have questions, we will have them now. If you haven't emailed them yet, you still have a chance. And with that, I thank you for your attention. Thank you.
Thank you, Andrey, once again for a great presentation. I just wonder if you could show the slide, which is the entryway into the GitHub site. At the bottom of the page, I've just noted where Sandra had shared information about Victoria, our users group, and that there are other users groups as well. And I just want to show people that. So if you have things to share in terms of resources or comments about the resources that Andrey is providing, questions, etc., you could add something here as well. It's just another way to communicate with our group and share resources. And thanks again, Andrey, for putting this site up. It's a great tool for everyone to have.
I have a question that I'm trying to articulate here. My sense is that many people, when they do an analysis, they have an idea, they have a plan in advance. They're going to look at a particular model, they run their model, they evaluate it, and then they write their paper. So although I think in reality we do end up estimating more than a single model, usually because we discover we've completely forgotten some important detail or we've made an error or whatever else. I wonder how many people are reacting to what you've just presented. I find it very interesting. And reacting, yeah. Because I don't know if most people would find themselves doing 50 models, and whether people might imagine that, well, then we get to the point that we might be capitalizing on chance. Now, if you come from the perspective that one finding from one study is not the answer, it's just a piece of a puzzle, and that we will then replicate and we'll look maybe at a similar series of models in another set of data. I just wonder if you can explain how you're thinking about modeling. I mean, I see what you did as a completely acceptable and appropriate way to proceed, but I wonder if some people think otherwise, and whether there's a way of explaining why you would do it this way, as opposed to saying, well, you know, I think many of us in our first stat courses are taught, well, A, don't peek at the data, and B, run what you say you're going to run, and then you're done, which is a very, very, very different way of thinking about modeling than what you presented this morning.
Just to quickly follow up, it is that tension between exploratory analysis and confirmatory analysis, and also that great fear of overfitting the model to the data. And I think that's kind of driving a lot of this tension and a lot of this concern. So I think the points that Andrea made are certainly relevant. And I guess the other point before you respond is in the context of reproducible research, of replication, where we really have the opportunity to not just replicate once, but many times within the IALSA research network across various studies. Does that remove this problem, this tension? So anyway, I think we can have a broader discussion, but good to hear a response.
So I think this frame of mind where you set on a model and you decide to go and you do it, and that I think that, first of all, it's really acceptable in the student situation, right? Because you might not have a mastery of anything else, and you know, sort of this is all the tools you have, and you sort of do it, and that's fine. However, from this one of the papers that I've mentioned before by Joe Rogers, that really talks about the pedagogical shift, paradigm shift, in which instead of teaching this procedure that you master and then you try to find the situation in which that procedure would work. So you would, have 101 statistical tests on your shelf that you will, find the right one and apply. Maybe that's a remnant of that, amplified by the fact that it's difficult to arrive at the point where I don't care what models did. I just, go and do that. You have to do a lot of those exercises to get to that point. In terms of capitalizing on chance, I don't think that this is the proper way to describe it, because what happened, I think it's going to be very expensive to just throw in every possible model that you want to fit and see what happens. The one example that I've shown, I had only one predictor in that model, but because there's so many minute ways that you can formulate the model, I'm not fishing for something. What I'm doing is I'll show you an example of a decision that I'm trying to get to. Each web page is like 45 megabytes, so because of all the graphics, it takes a while.
You provide many good examples of very open science. So this is all available up on a website.
Yeah.
All the products of your dissertation. Okay.
Well, yeah, this is. I'm getting. Okay, so this is the example that I was hoping to illustrate. So we have different color is a different index, AIC, BIC, and deviance. So deviance is this raw, unadjusted misfit that we're trying to see. Well, of course, if we're going to fit more complex models, the deviance is going to go down because we're overfitting it. At the same time, AIC punishes the model for complexity, right? So if and BIC, in addition to the punishment to model complexity, also punish it for the large sample size. So we have two different adjustments. So we can study the behavior, and that's why I said, okay, we have this stretch of models or series of models that we understand how that model changes, how that model evolves, and we're trying to understand at what changes in the development of model lead to a particular behavior in terms of its misfit. So see that, for instance, here as we add more and more predictors to the second order, we see that this deviance goes down invariably, but this BIC begins to go higher. It means that the model complexity that we add to our model is not compensated by the sample size, right? So that's an indication to us, oh, the BIC stops increasing. This is the deflection point. This is the point that I need to look at. But the AIC does continue to decrease with increasing model complexity, but sort of levels out. So what I'm advocating is not capitalizing on chance, but having access to the entirety of the analytic information so that you can have quick and immediate access to the information that you need. And sometimes you would just need to check that information is nonsensical. And that's all you need to check, and that is already very valuable. But people don't go through this trouble, don't estimate all the models that they really should be estimating because it's costly, because it takes a lot of programming effort, but it also takes a lot of attention. Can you imagine 10 model printouts and you were asked to evaluate them on, each model has, 20 different indices, so that's 20 dimensions, and you're trying to make sense of it. How are you going to make sense of that? This is what I'm saying. You need technology to come to your aid to help your attention, right? We're equipping our attention so that it can better focus on the tasks that we want to focus. I don't see why we should focus on matching the output, right? That's an enormous waste of human attention resources that could be utilized. So the effort of what I'm trying to advocate for is how can we outsource cognitive strain to the technology that supports our modeling effort.
I think that's excellent. I think certainly, again, in the context of the IALSA project, we're often evaluating complex hypotheses, often including the entry of different blocks of variables and looking at how these add additional prediction, and also of the interactions. And the interactions can get quite complex, and so that also becomes part of this model evaluation. Do the interactions add additional predictive value? And how do we contrast them across these different submodels? I think it's very important, and I think it's a very elegant way to bring this together in a very efficient way, because compounding the analysis of any one study, as you're beginning to now analyze 4, 5, or 10 different studies, being able to automate and to develop routines for this is just very, very helpful, very, very much needed here. So.
And I like the idea that really no project in science is ever done. So, for instance, like if we like moving to Bayesian, right? We do a study, and 50 years from now we realize that we have much better estimates on the priors, and that changes, so we can go back, pick up where we're going, and so the knowledge is really never lost. We just let it be unused for a while until we have a particular need. So that really allows us to accumulate knowledge at a greater pace and not lose stuff.
I was just going to say, these things are only as good as our analytics are half decent, because we're using them. And so instead of having the hypothesis or driven analyses by some hypothesis, we have these analytics which tell us something. So as much as they are okay, then we can go on and do all these different things and teach in a different way and learn in a different way.
Yeah. And another caveat, so for instance, this model sequencing, that I call it, there is no recipe. Like it's almost like 50-50 art and science, right? You don't know what you're going to end up with. You have to create something and then make sure that it's okay, and then convince others that it's okay. And you may fail at every moment. So yeah, and I don't think that there will be like very developed templates, because every project is so different. That's why you have to be flexible. That's why you want to find various ways to express the same principle, the same relationships, so you can pick and choose the expressive language that suits your projects.
I'd just like to follow up on that. I think we need to be careful about talking about whether we're guided by hypotheses or not, because I think what you're presenting is guided by hypotheses. You're just acknowledging that even though you have a general hypothesis about what variable might predict some other variable, there's details. For example, do we think that if we're looking at the idea of growth, do we think that individuals might start at different points and they might increase at different rates? And do we need to acknowledge that in the model or not? And so the model's kind of telling us, well, this one number is adequate to represent everyone, or yeah, it's the mean, but we should really be saying, we should be allowing individual differences in that model. So I think we're not throwing out hypothesis testing. We're just saying, all right, there's a limit to what we can hypothesize, and then we also, what are we trying to do? We're trying to find patterns in the data. So how can we best represent that pattern in the data that's complementary to the, or not complementary is not the right word, but that fits underneath our hypotheses.
Thank you.
That's
It's that tricky connection between theoretical model of change and statistical model. How are you going to prove that you got a match? Well, the proof is as good as your argument, so you're going to utilize everything you want.
I really like this topic, and just to follow up further discussion, going a bit away now from our workshop here, but this idea of reproducible research and how we come at answering a question. When you look at the literature on any one topic, there's within the same kind of question, there's many different ways that people have approached that, and so there's many different ways to formulate a hypothesis or a test of that previous finding. And so, again, it is a question of model. It's a question of comparing different models. And, so I think this is another important area in reproducible research, the fact that we approach answering questions with different models. And these are in the literature, these are in our state of science. And we really rarely do evaluate them against one another and say this is a better model. This answers the question in a better way or in a different way. And I think that's kind of where we're at too in our science. And I think you've hit on a number of these issues and these topics and shown us some ways forward. But I think we need to keep thinking about what we're all told what it means to come to a question in a more confirmatory way. Be explicit in what you're testing. But the problem is we can come at that in so many different ways, and we're going to end up somewhere different because of where we started. And so I think there's real value in evaluating it within the broader model context, both within the variety of terms you can fit within any particular model, but also in the variety of models. So I think there's that fuller context as well.
Just a reminder to our online audience, I know there's a lot of questions that are coming from the in-person site here, but you're quite welcome, and we encourage you to send us your questions via email, either right now or in the near future, because we'd like to hear from you. Thanks.